Hey everyone, my name is Miss Hu and I am a physics teacher. In this video, we are going to be learning about heat capacity and specific heat capacity. For those of you who are not familiar with the way I teach, I'm using Jamboard because I'm more of a whiteboard or blackboard kind of teacher. I don't really like to use PowerPoint presentations or similar. And that's because I'm a doodler and I like to write stuff and scribble stuff so that as I'm teaching, you can actually see the thought processes that are required to understand that particular topic. And in turn, it helps you remember and recall the concepts better. So by the end of this lesson, we should be able to define heat capacity as well as state its formula. And the same thing for specific heat capacity, its definition and its formula. And let's get started. So I've put it side by side so that you can see the difference. Let's talk about heat capacity first. So first of all, to understand heat capacity, let's have two different objects. Let's put up the same material so that it's easier to understand. And these materials have different masses, of course. So I'm just drawing them visually here so that it helps you with your understanding. And let's supply these two objects with the same amount of heat. So the arrows I'm drawing here are representing the heat energy that's being absorbed by these two objects. Now, because they have the same material, for example, they could be both made of copper balls, for example. So they have the same material, so material is not a factor in this case. But because they have different masses, obviously they will have different increase in temperature, correct? So let's think for a moment. Which object do you think will have a greater rise in temperature? That means assume both of them have the same starting temperature. Both of these objects are absorbing the same amount of heat, but logically, are they going to have the same final temperature? No, right? For obvious reasons. So, which one do you think will have a greater rise in temperature? That means if they both start from the same temperature, which will have a greater final temperature? That's right, the smaller one, right? So, heat capacity is the amount of heat energy needed to change the temperature of an object. So, the proper definition for heat capacity is this: it's the amount of heat energy needed to change the temperature of an object by 1 degree Celsius or 1 Kelvin. Because you have to remember that in physics, whenever we look at certain physical quantities or certain properties of an object or a material, we need to look at how the value changes per unit. In this case, it's per unit temperature, and the temperature can be expressed as 1 degree Celsius or 1 Kelvin. Now, Kelvin is, of course, the SI unit, but for the topic of heat, it's actually acceptable to express the unit in degrees Celsius as well. The reason for this is because the change of 1 Kelvin is actually equal to the change of 1 degree Celsius. So in terms of the formula, based on this understanding, if we look at the amount of heat energy absorbed, and for the heat concept, the symbol that's used to represent heat is Q. So it's not E or H. If you're wondering why this goes way back, we don't have to go into the history of that. But just understand for now that Q represents quantity of heat. Now remember that it is not the final temperature or the initial temperature that we're looking at. We're looking at a change in temperature. So that means we're looking at how much the heat supplied causes that change in temperature, because that's related. So how much heat supply causes that temperature change? We will express this temperature change as change in theta. So for those of you who are not sure what a triangle means, in mathematics, the triangle means the change of or the difference in. So for example, you would calculate the change of temperature as the final temperature, I'll write it short form, minus the initial temperature. So this is the change in temperature. So the formula for heat capacity can be expressed this way. Heat capacity is equal to the heat energy supplied or transferred, I'll just write it as heat energy, divided by the change in temperature. Make this into a fraction. I'll just add a line here. And I think for better visual And I think for better visuals, let's make this center. Yeah. Or if we were to express this with the symbols, now heat capacity is normally expressed with the symbol capital C. So we can also write it as C equals to Q over change in temperature. So the unit for heat capacity can be expressed based on this formula. So Q, as we know, is heat energy, and that's joules, of course. Change in temperature can be degrees Celsius or it can be Kelvin, which means that heat capacity is expressed as joules per degree Celsius or joules per Kelvin. Let me write it over here. So it's joules per degree Celsius or joules per Kelvin. To help you understand this a bit better, and let me go to the next slide first. So I'll just draw a separator here because we can also use this slide to compare specific heat capacity. So for example, if we were to look at those two objects again, say for example, because this object is much larger, it has a lower change in temperature. So let's say in both cases, we supply the same amount of heat, which is equal to 1,000 joules each. Let's say, for example, this larger object has an initial temperature of 25 and it goes up to, well, maybe about 30 degrees Celsius. And say for the smaller one, it also starts at 25. So because the ball is so much smaller, it has a higher final temperature. So let's say it goes up to maybe about 75 degrees Celsius. So in order to determine the heat capacity values, in this case, you can see that the change in temperature is only 5 degrees Celsius, whereas the smaller ball has a change of temperature of 50 degrees Celsius. So if we were to calculate the heat capacity for these individual objects, it would be, in this case for the larger one, 1,000 joules over 5 degrees Celsius, which gives us 200 joules per degree Celsius, whereas for the smaller object, it would be 1,000 joules divided by 50 degrees Celsius, which gives us 20 joules per degrees Celsius. So as you can see, based on these numbers, the smaller the number, the less heat needed to change its temperature. That means you need to imagine it this way, what the numbers mean. For the larger object, in order to increase its temperature by 1 degree Celsius, you need to supply 200 joules of energy. But for the smaller one, to increase its temperature by 1 degree Celsius, you only need 20 joules of energy. So for the smaller one, for example, you want it to go up by 2 degrees Celsius, you need 40 joules of energy only. 3 degrees Celsius, you need 60 joules. But for the larger object, you need more. So if 1 degree Celsius is 200 joules, for 2 degrees Celsius, you need 400 joules. 3 degrees Celsius, 600 joules. So heat capacity is just a measure of how much heat needed for that every 1 unit change in temperature. That means every 1 degree Celsius or 1 Kelvin, how much heat energy is needed to be supplied. So the larger the number, the more heat is needed for that change in temperature. Let's go back to the previous slide. Now, heat capacity is just in general. It only looks at each individual object. It doesn't look at the material or the mass. It's just this object, this is how much heat energy is needed for that change. Let's take a look at specific heat capacity now. They may look the same, but they're not the same. The addition of the word specific makes all the difference in the world. The moment we have the word specific here, think of it this way. This is the value of the heat capacity specific to the material. So, specific heat capacity, let's get straight into it. The definition of specific heat capacity is the amount of heat needed to change the temperature of a 1 kilogram substance by 1 degree Celsius or 1 Kelvin. Now let's talk about 1 kilogram in this case. So what you need to understand about specific heat capacity is that as long as they're the same material or substance, the value is the same. So no matter what mass you have, the value is the same. Let's take water. You could have a cup of water, you could have a pail of water, a bathtub full of water, a swimming pool of water, or even water that's as large as the ocean. But in all these cases, we would take a 1 kilogram sample from each of these, and then we compare. No matter how much you have, because we're taking the same baseline mass sample, 1 kg of each, you'll find that they will all have the same value. Specific heat capacity is specific to the material. So the formula for specific heat capacity is a little bit different from heat capacity. The symbol to represent specific heat capacity this time is the small letter C. And the formula for this is modified from heat capacity, which in this case is small c, equals to Q over M change in temperature. So Q is still representing the heat energy supplied or transferred. Change in temperature is still represented with the triangle theta symbol. Now what's different here is the addition of M, which is mass. So small c, specific heat capacity, and if you look at the formula, you'll find that the unit is developed this way. Heat is joules, mass is kilogram, and change in temperature, as mentioned earlier, can be in degrees Celsius or can be Kelvin. Hence, the unit for specific heat capacity is joules per kilogram per degree Celsius or joules per kilogram per Kelvin. So it's joules per kilogram per degree Celsius or joules per kilogram Kelvin. Another way to write the unit instead of putting in a bracket is to put the index of -1. So you can also write it this way: joules per kilogram per degree Celsius or joules per kilogram per Kelvin. So remember what I said earlier. Whenever we look at physical quantities or properties of a material, we also want to look at per unit. So not only are we looking at it as a per unit change of temperature, we're also looking at it from per unit mass, which in this case is per 1 kilogram. Here's another way to understand the difference. Specific heat capacity, because it's very specific to the material, that means no matter how much of the material you have, the value of specific heat capacity is the same. It's like how density is specific to that material. For example, if you look at wood, you could have a small wooden block or a large wooden boat, but the densities are the same. Now you put them both in water, the small wooden block or the large wooden boat, both of them are still going to float in water because the density of wood is less than the density of water. No matter how much you have of it, it's going to float in water. On the flip side, you could look at iron. You could have a tiny block of iron or a large block of iron. Put both iron pieces in water and they're both going to sink. So for the smaller, hey, it's so light, it can still sink. Why? Because the density is greater than water. No matter how much you have of that material, because the density is greater than water, it is still going to sink. So specific heat capacity is very unique to the materials, which means that each material already has its own value of specific heat capacity. And yes, these numbers are known. Here's a list of specific heat capacity values of common materials, and as you can see, these numbers are already fixed. These are the numbers that the scientists have already researched and found to be true, and these numbers are accepted as the scientific fact. To elaborate further so that you can understand specific heat capacity a little bit better, what I'll do now is I'll just take two materials for comparison. Let's take water at 4200 and aluminium at 900. So I'm just going to backtrack to this slide for your understanding. So let's say we have water. I'm just going to put like a square here because my drawing will probably scare you away from this video. So let's say we've got some water here, and let's put aluminium. So I'll color this a little bit differently. Yeah, aluminium's a little bit silvery, so let's imagine this is silver. And let me label this for you. Let's say this is 1 kilogram of water, and this is 1 kilogram of aluminium. For the sake of understanding, we'll put them as the same mass, because if we put them different masses, it's difficult to have the comparison. Now we can see from the values listed just now that water has a specific heat capacity that 200 joules per kilogram per degree Celsius, whereas aluminium has a specific heat capacity of 900 joules per kilogram per degree Celsius. What this means is quite similar to our understanding of heat capacity just now. The smaller the number, the less heat energy you need to change the temperature by 1 degree Celsius. In this case, the number is for that material. So if you have 1 kg aluminium, you only need 900 joules of energy to increase its temperature by 1 degree Celsius. But for the equivalent mass of water, 1 kilogram, you need to change 1 degree Celsius temperature, you need 4,200 joules of energy. That means water needs a lot more heat energy compared to aluminium if you want to change its temperature. So what does this mean? That means if you supply the same amount of heat energy, aluminium would have a greater rise in temperature. And what does this translate into physics? That means this would be a better heat conductor compared to water. That means water is a poorer heat conductor in comparison to aluminium. So once we understand how the values of specific heat capacity represent the heat conduction of materials, it makes it easier for us to select the materials in terms of the application when we're building objects or we're building devices, and we need to take into consideration thermodynamics. So for example, if we were to look at a cooking pot, this explains why the body of the pot is made out of material with low specific heat capacity, because we need the pot to heat up quickly in order to transfer the heat to food so that it heats up quickly. But we want to be able to hold the pot so that we don't burn our hands, right? This is why the handles are made out of materials with high specific heat capacity. So now that we understand how specific heat capacity is applied, so when it comes to physics, although heat capacity is important, we will focus more on specific heat capacity because this is the value for the material. So when we choose applications, we're looking at materials now, we're looking at the values of the specific heat capacity. Heat capacity, it does not apply to materials. It's just for this object. This object, how much heat energy needed to change the temperature. So while heat capacity may be useful in calculating the values for that particular situation, when we're looking at it in terms of general applications, we need to focus on specific heat capacity. So physics students, it is important to know both, but focus on specific heat capacity. This is why when you look up the values, you cannot find values of heat capacity of materials. You will find specific heat capacity of the materials. Now, how to use a formula in problems and calculations, I'll do that in another video. So one more thing before we end this lesson, we're going to take a look at the formula of heat capacity and specific heat capacity side by side. So I'm just going to cordon off this area so that this is where we would draw the formula. Let's take the heat capacity formula. I'll do this in yellow. So we have heat capacity C equals to Q over change in temperature. And we have specific heat capacity. Let me write this in blue. We have small c, specific heat capacity, equals to Q over M, change in temperature. Now, of course, you can see they're not exactly the same. Specific heat capacity has mass inside, but we can relate heat capacity and specific heat capacity this way. So what we can do is we will rewrite this formula. So we get Q equals C, change in temperature. And for specific heat capacity, we'll rewrite this as Q equals MC, change in temperature. If these Q's are the same, we can combine them this way. So you can get C, change in temperature, equals to MC, change in temperature. Of course, if the change in temperatures are the same, when you cut them off, you will get C equals to MC, which means that another way to calculate heat capacity is by taking the mass of the object multiplied with the specific heat capacity of the material. If we were to compare the units, they will work out as well, because if mass was kilogram and specific heat capacity is joules per kilogram per degree Celsius, cut, you will see you get joules per degrees Celsius. So what I'm showing you over here is that actually, if you would like to calculate specific heat capacity, there are two formulas. You can use this formula, or you can use this formula. This formula here is relating heat capacity with specific heat capacity. Which formula you would actually use, of course, depends on the question. and what information is provided to you. But whichever the case is, these are just the different options and the different relationships between heat capacity and specific heat capacity. For now, I hope you understand the difference between heat capacity and specific heat capacity in terms of their definitions and their formula. Thank you for watching, and I hope you found this video educational and helpful. Don't forget to click like and remember to subscribe to my YouTube channel, Physics Rocks, for more video lessons just like this.